Hello everyone. This is our first live discussion for this quarter. I hope you watched the discussions that I uploaded before. Today I will be going through three problems. The first one is a reduction of a block diagram. The second problem we have will be the linearization problem and computing the step response of the linearization, and then we will implement the MATLAB solution or numerically simulate the linearization and the nonlinear system using MATLAB's ode45, and then finally we will solve a similar problem to one of the homework problems that you had before. So let's start with the block diagram reduction problem. So there are two methods to reduce a block diagram. The first one is through graph manipulations, where when you have this is not my favorite method, but there are some rules that you can find in the book where you can simplify parts of the graph. Like for instance, we have let's see. Suppose that we have this entire block. Let's call this entire block this whole thing, let's call it G star. Then we would have a simpler block diagram that looks like something like this. G star, and then we have feedback with H3, and then this goes up, something like that. This point is this is plus, so we know that there are the rule for this, or the transfer function for this part is G star divided by 1 plus G star times H3. So, and then there are also other rules where if you have if you have G3 plus G2 as a transfer function, you can split it into G3 and G2. And then you can sum them together, and so on. So these primitive, we can use these primitive rules to simplify. There are other rules as well that we can use to simplify a graph of like this. However, this is not my favorite method because it's not systematic. So the systematic method that we're going to do today is the one that that is adopted by Professor Marco, which is as follows. Let me erase this. First, we look at the number of summation junctions that we have in our diagram. In this case, we have 1, 2, and 3. Then we name every signal that comes immediately out of the summation junction. So we have x1, x2, and x3. Then we try to express x1 and x2 and x3 in terms of each other, r and y. So the first equation we have is x1, because it comes out of the summation junction. We know that x1 is going to be equal to r minus whatever this signal is. So if we trace this signal back, we see that it is multiplied by h3, and then we see that it's equal to h3 times y. So our first equation is x1 is equal to r minus h3 times y. The second equation is x2. We have x2 is equal to g1 multiplying x1 minus whatever this branch is. So this branch is h2 multiplying g3 multiplying x3. So this is the second equation. And finally, the third, not finally, the third equation is x3, right? We see two summation junctions, or two signals into, going into the summation junction. So we have g2 multiplying x2 and h1 multiplying y. So this is the third equation. And finally, the fourth equation, which is the equation for the output, is simply equal to g4 times g3. So this is the fourth equation. So we have four equations, and typically the way to solve them, we want to obtain a transfer function between r, or transfer function from r to y. So typically what we do is we substitute from one equation into the other. For instance, if we substitute with x1 into the equation for x2, we get this expression here, g1 times r minus g1 times h3y, because x1 is equal to this, so we just substitute, we get this expression. Then if we substitute with this expression inside, so this is now x2. If we substitute with this equation into the third equation, we get this equation here. Okay, again, it's just direct substitution. So now we have an equation that on both sides contains x3. So we solve for x3. Basically, we move this term to the right-hand side, and we take x3 as a common factor. Then we divide by the coefficient that multiplies x3. We get this equation here. Then we substitute with that expression in the last equation for y to obtain that y will be equal to this. We obtain an equation with both sides containing y. So we move one of them to remove this term. We move this term to the right, and we solve for y. We get this expression. So this y is equal to this multiplying r, which means that the transfer function, or that represents the reduced block diagram, y divided by r, is equal to this expression. Any questions? Okay, I hope that was clear. Now we move on to the linearized equation. We would like to solve or to linearize this differential equation around the point x0 equal to 1 and x dot equal to 0, and then we would like to compute the response due to initial conditions of delta x0, which is the initial condition for the perturbation or for the state of the linearization. We want that to be equal to some epsilon that is bigger than 0, and delta x dot, which is the velocity of that one, is equal to 0. So first we notice that the nonlinear term here is the x cubed. Okay, and so this can represent, for instance, a spring or a softening string um, because we have x. This can be thought of as the traditional spring. And then we have x cubed, which is a term that that is dominated by x when x is less than 1, but dominates x when x is bigger than 1, right? Because if we know that if x less than 1 implies that x cubed is less than x. But if x is bigger than 1, we know that x cubed is definitely bigger than x. Right? So let's see what happens when we linearize the system. So first we let y equal to x dot. X dot is the velocity. And so this means that y dot is equal to x dot dot, which is the acceleration. And from the equation of the system, this will be equal to negative x plus x cubed. So this means that x dot and y dot, this system will be equal to y, um, the vector y, and or the scalar y in the first entry of the vector, and then we have negative x plus x cubed. So the linearization, we basically compute the Jacobian of this vector, right, which is over here. So let me call this the Jacobian. So to compute the Jacobian, we compute the partial derivatives of the first entry of the vector with respect to our coordinates. In this case, they are x and y. So partial y by partial x is 0. Partial y by partial y is equal to 1. And then we compute the partial derivatives of the second term. In this case, it's this by partial x is negative 1 plus 3x squared. And then partial this by partial y is equal to 0. Then we evaluate with the point that we would like to linearize around, which is x equal to 1 and y equal to 0. In this case, we will get that the linearized system, which has this state delta x dot delta x and delta y, it is equal to or is given by delta x dot and delta y dot equals to 0, 1, 2, and 0, multiplying delta x and delta y. So if you want to go back from a vector equation to a linear differential equation, we can we see that delta x dot is equal to delta y, right, from the equation, which means that delta y dot is equal to delta x double dot, which from this equation we see that it's going to be equal to 2 times delta x, which means that delta x double dot as a function of time minus 2 times delta x of time is equal to 0. So this is the differential equation for the linearized system. And we would like
I
to...
just had a quick, sorry.
Yeah, go ahead.
In the line above, did you mean the delta x and delta y, or are they supposed to be dotted? Because I noticed the right side also has delta x and delta y. It seems like that shouldn't be
Where?
true. And the right side of the equation above the yellow.
This one?
Yeah, yeah. So are the left and the right side both just regular delta x and delta y like that?
Yeah, so delta x dot is equal to this matrix, this vector, okay, is equal to this matrix multiplying this vector.
Right, so it is dot, because it doesn't have...
Yeah, it is a dot.
Okay, because it just had it doesn't have the dot there on the left side.
No, on the left it does have the dots. These are the derivatives, the time derivatives of the functions delta x of t and delta y of t. These are the velocities of these two functions.
Okay. I just mean that I see it written there without the dot on the.
On what?
Right, just to the left of where your cursor is, I think. Right.
So this is matrix multiplication.
Oh, okay. Sorry, I see now.
Yeah. Okay. Okay. So let's continue. Yes, so this is the second order differential equation that governs the evolution of the linearization. Okay, we have the delta x double dot minus 2 times delta x is equal to 0. So we would like to compute the response of this system due to the initial conditions. Let me go back, which is delta x 0 is equal to epsilon, which is something bigger than 0. H, it doesn't matter. We can just say that it's not equal to 0 for now, and delta x dot 0 is equal to 0. If we apply Laplace transform to this equation, we get, let me do an abbreviation here. Let me say that Laplace of delta x of time is going to be equal to x of s. Okay, so using the Laplace rules that we know, we have that delta x double dot, the Laplace transform of that is going to be equal to s squared multiplying x, right, which is the Laplace transform of delta x, and minus s multiplying the initial condition for the velocity, which in this case is going to be equal to 0, minus the initial condition of delta x, right, which is in this case going to be equal to epsilon, and then we have minus 2 delta x, which will have the Laplace transform of minus 2x of s. All of this is equal to 0. So if we move things aside and solve for x of s, we will get that x of s is equal to epsilon divided by s squared minus 2, right? So this is a second order factor. We want to factorize it into two first order factors, right? So if we just take epsilon as a common factor and do a partial fraction expansion, we get two terms, s plus square root 2 and s minus square root 2, each with the two coefficients a and b. We can use the traditional method for solving the coefficients in a partial fraction expansion. In this case, we see that a multiplying s minus square root 2 evaluated at s equal to negative square root 2 will be equal to 1, which implies that a will be given by this fraction. And similarly, we do the same with b to get that b will be equal to this fraction. So now we have, now that we have a and b, we can do the inverse Laplace transform. So, do inverse Laplace in order to obtain an expression for the function delta x, the function of time, which is this here, right? I think there's a minus sign. There's a minus sign. So we see that whatever epsilon is, and as long as it is not equal to 0, we will have a term that is going to blow up, right? Because of this positive exponent in the exponential term. Whatever whatever epsilon is, as long as it's not equal to 0, this linearization is going to blow up. So blow up means that it's going to go to infinity. Okay. However, it's important to understand the difference here, because if the linearization goes to infinity, this does not imply that the actual system will go to infinity. And to understand that, let's try to linearize around, or I will leave you guys to do this. Try to linearize around x equal to 0 and x dot equal to 0, okay, instead of x equal to 1. Try to linearize around the origin and simulate the linearization and the original dynamics with an initial condition of, let's see, the initial condition of 1.1 and initial condition of 0.1. To see what will happen for the actually just the initial condition of 1.1, simulate the linearization and the original nonlinear dynamics with these initial conditions. So now So now we're supposed, or I will go cover the MATLAB simulation of that, but first let's finish the third equation or the third problem that we have, and then we will move on to MATLAB. The third problem, we are given that an input R of t equal to sine of t was applied to a black box equation, or a black box system with some transfer function g of s. Okay? And we assume that this transfer function is linear. And the output response, starting from 0 initial conditions, was observed to be this expression. Okay. And notice something, which is that even though we applied a sinusoidal input, which is an oscillation, we applied an oscillation to the to this black box, our response is devoid of any, or does not contain any oscillations. Okay, this will turn out to be important later on. I would like to determine the transfer function of this system. So the solution of this is very simple. We know that the transfer function is the transfer function of the system is equal to the Laplace transform of the output divided by the Laplace transform of the input at that particular right. So we have an expression for both the input and the output. We can simply compute their Laplace transforms and divide them to get the transfer function. So the Laplace transform of the input is 1 over s squared plus 1, right? This is a sinusoidal function. Its Laplace transform is given like this. And Laplace transform of the output, we have 3 exponentials, right? Each one with a exponent of 1, so we have 1 over s plus 1, and then minus 6 times s plus 2, and then plus 1 over s plus 3, we can do like we can collect everything under a common denominator, and we simplify, so we get that the Laplace transform of the output is going to be equal to 6 divided by s plus 1 times s plus 2 times s plus 3. Okay, so now g of s is going to be equal to y of s divided by r of s, um, which which means that it's going to be equal to 6 times s squared plus 1 divided by this expression. And notice that we did not get any s squared, or that we got an s squared plus 1 in the numerator. Okay. Now, let me ask you this question and see if you can figure it out. Can you guess why we did not get an oscillation in the output, even though we applied an oscillation to the input? From the look of this transfer function. I'll let you think about it for 2 minutes. I mean, just maybe right back. Anyone figured it out?
I remember the point that if there's no, like, the imaginary roots are what makes the output sinusoidal. Do we not have any imaginary roots?
Yes, we don't have any imaginary roots, but why don't we have any imaginary roots? You are correct, but there's an interesting thing that happened that did not allow any imaginary roots to appear.
I'm not sure.
So this is the transfer function, right? This is the expression for the transfer function. If we try to compute the output, what do? We multiply the transfer function with the input, right? What is the input?
The input is FT, or the Laplace, right? Yeah.
Right, 1 over s squared plus 1. So s squared plus 1 cancels with s squared plus 1 in the numerator. And so if it did not cancel, if this, for instance, was s squared plus 5, they would not cancel, right? And then when you do a partial fraction expansion of this, of the transfer function of what you get here, you will get imaginary roots, right? Because this factor s squared plus 5 will not go away. But it so happens that the input was exactly at the same, was the same as the factor in the numerator, right? So they cancel with each other, and we don't get any any imaginary roots. So we don't get any oscillations in the output. So can you think of an application where this might be useful? That we have some system that that we would like to completely ignore a particular oscillation, or an oscillation at a particular frequency. We wanted to completely ignore this oscillation so that it does not appear in the output.
Some sort of like isolator or
Exactly. So, for instance, if we have a car, right, the suspension system of a car, if we have a car that is walking on a bumpy road, and we would like to be able to damp these oscillations so that the passengers don't feel it, right? So in this case, let's suppose that this is a simple free body diagram of a one-wheeled car, and so we have this is the wheel, right, and this is the road. The road, if the car moves to the left, right, we can think of these bumps that they translate to functions of time, right, as a disturbance to the system of consisting of the car, the suspension system, and the wheel, right? The wheel is the terminal where the input enters, and we would like to isolate the oscillation from, or any oscillations at some particular frequency of ws to x of s, right? So the transfer function from ws to x of s is g of s, which is the suspension system, which is equal to n of s times divided by d of s. N of s is the numerator, and d of s is the denominator of this transfer function. If we somehow actively adjust the g of s as a function of this function, if we can somehow manipulate some parameters in this expression so that n of s, which is the numerator of this transfer function, multiplying w of s, which is this, in this case, it will be this oscillation at this particular speed, okay? If we make them approximately equal to 1, which means that they cancel each other approximately, and that the denominator is stable so that we don't get any unstable response, we would feel absolutely no oscillations whatsoever. So let me show you a nice video. Let me skip to the important bit. Yeah. The video is kind of laggy, right? Do you see the video clearly, or is it laggy?
Oh, I can see it.
So I left the link in the notes. I'm gonna upload them, but it's not very clear. I'm not able to show it clearly here, but it's a nice video that shows exactly this, or this concept that I wanted to emphasize. Okay, so let's go back, see what we have. Okay, so yeah, so now let's go try and implement this on MATLAB. So we need to use to simulate the solution of an ODE. We use the function ode45. Okay, so let's look at the documentation for that. So this function ode45, the simplest call of it, we require something called an ODFun, which is a function that represents the dynamics that we would like to simulate, or the ODE. Then we have tspan, which is the time span of our that we would like the simulation to happen, and then we have finally the initial condition. So the ODE, the function handle ODE, is a function handle that defines the function to be integrated, or basically the dynamics that we would like to simulate. For example, if we have this simple equation, y dot equal to 5y minus 3, then the corresponding ODE function would have to take t and y as inputs, and it has to output y dot as a function of these inputs. In this case, it's just 5y minus 3. In our case, so first we want to create a function. Let's see. Linear system 1 has to take, it's called fun, at t x, linear system 1, and yes, linear system 1 is equal to this, and returns a vector, right? The first entry in the vector is the second entry of the input x, and the second input is x minus x1 plus, no, just actually plus 2x1. That's the linearization that we computed at x equal to 1. Let me create another function, non-len system 1 is going to be equal to x. This is x2. This is minus x1 plus x1 cubed. We would like to solve this, right, using ode45. So we compute. First, we define a t-span. So let's call this t-span is equal to the length space from 0 up to 5 seconds with a spacing of, or 5, we have 100, totally number of 100 entries. Then we would like the initial condition to be, we can make it a very small perturbation, let's say 0.01. And 0. This is the initial condition, linear system x0, we call it x0 and 0, and then we have non-linear non-len system x0 is going to be equal to 1.1 and 0. So now we compute this x linear system x is equal to ode45 of linear system 1 t-span and linear system x0, and then we do the same, and then system x, all this done, and the same here. Alright, let's see, hopefully no errors. Okay, yeah. 2 more integration. Let's make this 2 seconds. Okay, very good. Then we want to plot t-span and linear system x. Let's make this bigger. Let's plot 2, 1, 1. this, and then some plot to 2 plot dspan none and system x.
Is the tilde that's part of the output vector is part of the syntax function, or is that
Is what?
the tilde like the first of your output
Oh,
bracket?
yeah. So this is just because the output of OD function will be the time vector and the corresponding.
Mhm.
Yeah, but because I already gave it the t span here, it's just gonna return t span again.
Oh, that's what that means. Just
Yeah.
use.
So yeah, it means that I'm not assigning whatever the output is
See.
in this slot. Okay. And we would like to obtain that. Well, we can just run this. So this is the response. We can increase the time a little bit, make it like 3. Let's see what happens. Yeah, the response actually blows up after. Let me say 2.5. Yeah, so we see that the nonlinear system actually has some fancy stuff here, like title of um, title. This is the linear system. This title nonlinear system. So we can mark this again. We see that the nonlinear system blows up very quickly. Like it cannot continue beyond 2.5 seconds, or it blows up between 2.5 and 3. System goes, the first state goes to infinity, whereas the linear system continues or can be simulated for further time. So this is the simulation for, or at least this is the syntax that we use for ode45. Okay. Now let's try to do the linearization and the linear system around x equal to 0 rather than x equal to 1. Okay. So the linear system is going to be different. In this case, let's call it linear system. Going to be equal to 2. And I'll let you do the details, but this is actually going to be equal to negative x1. Okay. And so this is linear system 2. The initial condition, the new initial condition for both is 1.1 and 0. Okay, and we would like to simulate this. This is 2. Same initial condition, and we do the plots. Okay, so if we run this, we see that the linear system actually we can continue the linear system for a very long time. Let me actually let me do it here. Let's see, t span 2 is equal to mid space 20 seconds with so 0 20 seconds, and 1000 entries. We can take span 2 and put it here. Then we simulate this. What's the problem now? This was mixing length. Oh, okay. This is 2. So we see that the linear system can be continued forever because the oscillations will continue forever, whereas the nonlinear system, of which the linearization should represent close, example actually blows up. Like if you try to continue beyond 2.5, you will get a warning saying the system could not be continued any further because the state actually blows up, goes to infinity. So the linearization can tell us some things about the nonlinear system, but it does not tell us everything, and it's important to keep that in mind. Okay, that's all I have for today. Does anyone have any questions? Okay, thank you guys for waking up this early to attend the discussion. I appreciate it, and I'll see you next week.
Thank you. Have a good
Have a
one.
good day. You too.